The Stephen S. Chang Award recognizes scientists or technologies who have made decisive accomplishments in research for the improvement or development of products related to lipids. Dr. Dharma Kodali is currently an adjunct professor in bioproducts and biosystems engineering at the University of Minnesota and a world-recognized expert in lipids and new product development. In 2010, he was named an AOCS Fellow in recognition of his contributions to fats and oils research.
Welcome, everyone. Thank you for joining us for the 2020 Stephen Chang Award Lecture, Chemical Synthesis as a Tool to Create Value in Lipid-Related Products. I am Alejandro Marangoni. I'm a professor and Canada Research Chair at the University of Guelph in Guelph, Ontario, Canada. I am delighted to introduce Dr. Dharma Kodali as the recipient of the 2020 Stephen Chang Award. This award recognizes a scientist, technologist, or engineer who has made distinguished accomplishments in research for the improvement or development of products related to lipids. The award is made possible by the Stephen and Lucy Chang Endowment Fund. Dr. Dharma Kodali is a world-recognized expert in lipids and new product development and has over 40 years of research experience in academia and industry. He's currently an adjunct professor in bioproducts and biosystems engineering at the University of Minnesota. Previously, he was a professor at the University of Minnesota and Boston University as well, studying the fundamental aspects of structurally defined lipid synthesis, molecular packing, properties, and their influence on metabolism and development of value-added products. His industrial experience includes working as a scientist and R&D manager at Cargill and as a senior principal scientist at General Mills, developing several new products from concept to commercialization. Still, his primary area of research continues to be developing value-added products from fats and oils and agricultural materials for food and many industrial applications. Dr. Kodali has authored over 75 publications and book chapters and edited 2 books on trans fats. He is an inventor, co-inventor of over 30 patents, and his accomplishments include Cargill's Chairman Innovation Award in 2001, the American Chemical Society's Industrial Innovation Award in 2002, the American Old Chemist Society T.L. Mounts Award in 2003, Alton E. Bailey Award in 2017. He's an active fellow of the American Institute of Chemists and, of course, an American Old Chemist Society fellow from 2010. He has served in the American Oil Chemist Society in various capacities, including chair, Industrial Oil Products Division, teaching short courses, associate editor and peer reviewer of JOCS, session chair at national meetings, and a member of Books and Publications Committee and Recognition Program Committee. Thank you very much for joining us. With that, I will turn it over to Dr. Kodali.
Good morning, everyone. Thank you, Professor Marangoni, for that kind introduction. First, I would like to acknowledge and thank AOCS for being an important part of my professional career for the past 40 years. Professor Chang, who instituted the award, was an immigrant and made numerous contributions to lipid research in both fundamental understanding and applications. He worked in industry and academia and was a prolific inventor and educator. In true spirit of Professor Chang's accomplishments, I am really honored and delighted that my research contributions have been recognized as unique and valuable, and that I join other accomplished and prominent lipid scientists who won the award before me. I would like to thank Professor Marangoni for nominating me for this award, and also other colleagues who supported the nomination. With that, my today's presentation is chemical synthesis as a tool to create value-added lipid products. Before I start my presentation, I want to dedicate the Chang Award presentation in memory of my mentor, teacher, colleague, and friend, Professor Donald M. Small. He is the one who introduced me to the lipid physical chemistry about 40 years ago while working in biophysics at Boston University. He is well known to AOCS community through his treatise, Physical Chemistry of Lipids from Alkanes to Phospholipids, and also he was the recipient of a Bailey Award. With that, my presentation outline is shown here. This presentation has two parts. In the first part, I'm going to talk about the fundamental aspects of stereospecific lipids, followed by the industrial applications. In the first part, in the introduction, I'm going to talk about the prochiral nature of glycerol, followed by the stereospecific glycerol derivatives, then the synthesis of stereospecific mono, di, and triacyl-glycerols by protecting with various protecting groups, isopropyldin, trityl, benzyl. Then deprotecting the groups, we faced some problem of acyl migration, and I will also show how we were able to overcome this problem. This is followed by the fundamental aspects of the stereospecific glycerol derivatives, their structure, molecular packing, and property relationships. Then whatever we learned here, how we were able to apply in the industrial applications. We chose two areas of applications. One is lubricants, the other one is plasticizers. I will give a couple of examples for the lubricants, cyclopropanated oils and heterogeneous oils, and for plasticizers, epoxy acetylide fatty acid esters, both which have been commercialized and not so successful as well. I will show both the examples. Then I will summarize my presentation. I would like to bring one other thing to the attention of the audience. The work I'm going to present, I chose that has been done in the last 40 years. I chose the highlights of some of the studies that fits into this theme, and I will highlight those studies. If anybody would like to have the further details, they can refer to the publications and patents that are cited on each slide. Here, the glycerol chirality is shown. On the left, the glycerol is projected in the three-dimensional space through the central carbon, with the primary hydroxyl-bearing carbons and hydroxyl are projected towards us. And when you look at these primary hydroxyl-bearing carbons, they are similar. Therefore, there is plane of symmetry that exists here, making the glycerol not chiral. However, when we substitute different esters at these primary hydroxyls, the plane of symmetry is lost, the glycerol becomes optically active. So the seemingly identical primary hydroxyl-bearing carbons are not identical. To differentiate them, the glycerol is projected on the right in a Fisher projection, with the carbons are numbered 1, 2, 3 when the hydroxyl is facing on the left side. To differentiate the stereospecific glycerol derivatives from the racemic mixtures, the SN is prefixed before the glycerol to indicate that they are stereospecifically numbered glycerols which are optically active. To make this point a lot more clearer, here I took the glycerol and esterified with two different fatty acids, palmitic acid and acetic acid. Then we get two stereoisomers, as is shown here, one palmityl 3-acetyl-sn-glycerol, one acetyl 3-palmityl-sn-glycerol, which are enantiomers, are not identical. That makes the point of glycerol, which is not chiral or prochiral, becomes chiral. With that, let me talk about the glycerol intermediates that facilitate the synthesis of stereospecific glycerol derivatives. Here I'm showing 4 intermediates which are key to the synthesis of various glycerol derivatives, which are protected with isopropyldin, benzyl, and trityl groups. I will show the synthesis of these intermediates followed by the various other glycerol derivatives. The synthesis of 1,2-isopropyl-SN-glycerol is shown here. The starting material for this compound is the D-mannitol, which has the right stereochemistry, is reacted with acetone in the presence of zinc chloride to protect the 1, 2, and 5, 6 hydroxyls with ketal groups. The vicinal diols in the middle are cleaved with periodic acid to give the aldehyde. This aldehyde is reduced with sodium borohydride to give the 1,2-isopropyl-SN-glycerol. For the synthesis of 2,3-isopropyl-SN-glycerol, the starting material is L-arabinose, which has the right stereochemistry, is derivatized into dimercapto compound by treating with mercaptoethanol, and then reacted with 2-methoxypropene to give the 4,5-isopropyl protected group. Then the vicinal diols are cleaved with sodium periodate, and then the aldehyde formed is reduced with sodium borohydride to give the 2,3-isopropyl-SN-glycerol. So to check the enantiomeric purity of these materials, we converted these isopropyl compounds to their benzoyl derivatives and separated them on a chiral column on HPLC. In the middle, the HPLC chromatogram shows the 1,2 derivative elutes first, followed by the 2,3. When we injected the racemic mixture, we could be able to separate them at the baseline. So both these compounds do not show the other isomer, therefore they are optically pure materials. With that, let me talk about the synthesis of 3-acyl-SN-glycerols. They are synthesized from 1,2-isopropyl-SN-glycerol by condensing with the appropriate fatty acid in the presence of dicyclohexyl carbodimide, DCC, and dimethylaminopiridine, DMAP, at room temperature. This esterification procedure is very efficient and mild, as it can be done at the room temperature. This is a standard procedure for esterification throughout. This 1,2-isopropyl-glycerol is converted to the corresponding ester, and then to remove the ketal, remove the ketal became increasingly difficult with the increasing chain length of this acyl chain. When the acyl chain length is shorter below the cysteine carbon atoms, we were able to remove it by treating with HCl either at room temperature or below. But as the chain length increased beyond cysteine, we were not able to cleave the ketal function. So increasing the temperature was not an option because we knew that acyl migration occurs. So we adopted a different procedure by applying this on a silica gel in a solid state. We passed a HCl gas at -75 degrees that was able to cleave the ketal function to get the longer chain 3-acyl-glycerols. So to check the purity of these compounds, before I go on, I would like to talk about the acyl migration. What is acyl migration? The acyl migration, which is shown here, the acyl function, which is an ester, if there is a adjacent hydroxyl present, jumps to that hydroxyl, making that acyl group to wander to the 2-acyl-SN-glycerol, and then from 2, it goes to the 1. So this acyl migration is known in both lipid and carbohydrate chemistry before this time. So we wanted to see what are the factors that influence this acyl migration are given here. Both the acidic and basic conditions enhance the acyl migration, and so is the nature of the acyl chain also influences, whether it is normal or branched, saturated versus unsaturated, and so on. And the smaller size fatty acyl chains migrate faster than the longer ones, and the higher temperature increases the acyl migration rate, and so is the liquid compared to the solid. So with that understanding, let me show you how this acyl migration happens. The mechanism of acyl migration is shown here. The acyl migration is initiated by the nucleophilic attack of the lone pair of electrons present in the free hydroxyl on the carbonyl carbon, forming the 5-membered cyclic ester ring, which is shown here. And the original ester linkage is cleaved to form the 2 acylglycerols. Under the acidic conditions on the top, the carbonyl oxygen is attacked by the proton, making this carbon electropositive, making that lone pair of electrons attacking the carbonyl more facile. Similarly, under the basic conditions, the base attacks the hydrogen here, the proton, and then it becomes a better nucleophile, making the acyl migration a lot more facile. So with that understanding, we have to employ more gentle conditions doing this synthesizing these stereospecific glycerol derivatives. So when there is an equilibrium that occurs during this acyl migration, what happens is shown here. If we start with 1 or 3 acyl-sn-glycerol, it goes to the 2 acyl-sn-glycerol and then to the 1 acyl-sn-glycerol. Once it reaches the equilibrium, the 1 and 3 acyl-sn-glycerols are equal in number, and that becomes optically inactive because that is a racemic mixture. However, at equilibrium, the ratio of the primary esters versus the secondary esters is about 9:1. So once we understand this, we wanted to see how pure these monoacylglycerols are. We were able to separate them, all of them on a HPLC column, as is shown here on a reverse phase. The carbon atoms in the 3 acyl chains are shown here. Under the same conditions of the HPLC, we were able to separate 2 and 3 isomers. As these 3 acyl-sn-glycerols do not show any of the 2 isomer, we do think these are all pure, optically pure materials. We published this work in 1985, but we were not happy with employing a strong acid, especially passing the HCl gas. We were not happy, so we were looking for more milder procedures, which when we went to the literature, we were able to find one published by Gwendon et al. The year before in 1984 in Journal of Organic Chemistry, the cleaving the ketol groups with dimethyl boron bromide. So we went and synthesized this reagent and then used it to decatalyze to produce the monoacylglycerols. It worked beautifully at -50 degrees. And this is not a strong acid at all. So we were able to use it on all, irrespective of the chain length, we were able to create the 3 acyl-sn-glycerols. So the compounds, both the 1 and 3 acyl chains, acylglycerols that were produced are shown here in very good yield, about 70 to 90% yields that is shown here. And all these compounds were optically pure, as is shown by the optical rotation of these materials. So with that, we were able to synthesize the monoacylglycerols. Now I will show how the diacylglycerols were synthesized. The 1,2-diacylglycerols are biologically active materials and are intermediates in many biological processes and are integral components of membranes. They are considered to be secondary messengers which bind and activate the phosphokinase C. So these are very important biologically. To synthesize these molecules, we started with the 3-benzyl-sn-glycerol. The 3-benzyl-sn-glycerol, how it is got is shown on the top. We started with 1,2-propylene isopropyldene S-glycerol, reacted with benzyl chloride to form the benzyl derivative. Then the isopropylene is cleaved with the acid by treating with the acid to get the 3-benzyl-sn-glycerol, which was reacted with the 2 moles of the fatty acid, required fatty acid. We got the diester derivative. This diester derivative, we want to remove the benzyl group. Usually that is done by hydrogenolysis. The hydrogenolysis procedure works very well for the saturated acyl chains. However, when it is unsaturated, they get saturated, therefore changing difficult to get the unsaturated diacylglycerols. So we were looking for a mild debenzylation procedure. And then we thought the dimethyl boron bromide, which we used for the monoacylglycerols, may work here. And actually we tried it, and a little bit at higher temperatures of -20 degrees, we were able to remove the benzyl group to produce the monoacid diacylglycerols as is shown here. With that, I would like to talk a little bit about the acyl migration in diacylglycerols as well, which we have studied acyl migration in diacylglycerols as is shown here in different mediums, in neat, in vesicles, and micelles, and so on. Okay, I got sidetracked. I will come to that acyl migration in a minute. Before I do that, I want to talk about the mixed acid diacylglycerols, which is shown here. The mixed acid diacylglycerols synthesis is a little bit complicated because we want to introduce two different acyl chains at 1 and 2 positions. To do that, the starting material is the 1-acyl-sn-glycerols, which I showed already. This compound, we would like to protect the one of these hydroxyls in the presence of the secondary and primary hydroxyls. That was done by reacting with the triphenyl chloride, which is a very bulky reagent that reacts with only the primary hydroxyl, leaving the secondary hydroxyl intact. This material then condensed with the appropriate fatty acid. Usually it is a unsaturated fatty acid because those kinds of materials are more biologically active. So we condense with the fatty acid to get to the 1,2-diacyl mixed acid diacylglycerols with the trityl group. The trityl group also fortunately worked well to detritylate with the dimethyl boron bromide at -20 degrees to give the mixed acid 1,2-diacylglycerols. With that, now let me talk about the acyl migration in diacylglycerols as well, which we studied in various states, including the neat, vesicles, and micelles, which is shown here. So 1,2-diacylglycerols, also the acyl migration occurs when we take the 1,2-diacyl-sn-glycerols, they transform into 1,3-diacyl-sn-glycerols, and at equilibrium, the ratio of the 1,2 to 1,3 are 44 to 56%. So once we have the mono and diacylglycerols, to synthesize the triacylglycerols is very easy because to put the third acyl chain where we would like, we have all the handle to put the different fatty acid chains esterified at the glycerol 1 or 2 or 3 or in any position. We synthesized number of homologous series of these triacylglycerols. One of them is shown here, 1,2-dipometyl 3-acyl-sn-glycerol, where the third acyl chain, showed as an X, is varied with even carbonatum fatty acids of 2 to 16 carbonatoms. So we studied this homologous series of compounds extensively. Synthesizing this homologous series of compounds is very important as we study their physical properties and molecular packing. The changes that occur systematically will show the structured molecular packing relationships. We did synthesize number of other homologous series as well, but for the sake of the time, mostly I will show the homologous series of PPX in this presentation. Now I am done with the synthesis part of this presentation. Now I will switch to the molecular packing and physical properties of these materials. Especially these long acyl chain containing molecules have the unique ability to crystallize into more than one crystal state. This phenomenon is called polymorphism. The classification of polymorphism is shown here, beta, beta prime, and alpha. This is based on the subcell structure, which is shown here. And this differentiation or characterization of these polymorphs can be done with powder X-ray diffraction, infrared or Raman spectroscopy. And especially the powder X-ray diffraction, the subcell structure. Subcell structure is the short on the short axis, how these zigzag chains are packed with relation to each other is the one that defines the polymorph. For example, in beta, these zigzag chains are in parallel configuration, whereas in beta prime, they are in orthorhombic perpendicular to each other, whereas in alpha, they do not have any chain-chain specific interactions, but they are arranged in a hexagonal packing, which is shown here. And the packing along the long axis is shown on the top. These molecules pack in a bilayer structure, as is shown here, with 2 chain lengths. Each of these polymorphs have different properties, which I'm going to show you how they differ from each other. And based on those properties, their functional properties also differ. First, for example, some of the properties are melting temperature of these materials. Beta is the highest melting polymorph, and alpha is the lowest. Beta prime is the intermediate one. If you look at the enthalpy, this is the highest enthalpy, and this is the lowest. This is intermediate. However, if you look at the volume, because of the loose packing of the chains, alpha is the highest volume, beta is the lowest, and beta prime is the intermediate. Because of these different physical properties, the functional properties such as hardness, texture, mouthfeel, graininess, lubricity, air entrapment capacity also changes between these polymorphs. If a food chemist is using these fat systems in some of their products, if they want to use any of these functional properties, they have to understand the polymorphic behavior of the fat systems is utilizing. That is the application part of it one can appreciate. With that, let me show you one of the molecules that have been synthesized, and its polymorphic behavior is shown here. The compound is PP10, that is 1,2-dipalmitoyl 3-decanoyl SN-glycerol. The chain length of the third chain is only 10 carbon length, whereas 1,2s are 16 carbon length. This compound crystallizes into 5 polymorphic forms, which are shown here. And 3 of them are metastable structures, alpha, beta prime 2, and beta prime 3. And more stable structures are beta prime 1 and beta. And beta is the most stable. As you can see, these 3 metastable structures, in these 3 metastable structures, the short acyl chain 10 packs along with the longer acyl chain C16 chains, whereas in these 2 stable structures, that shorter chain segregates and forms a middle layer in between the 2 palmitoyl layers. All these 5 different polymorphic forms have distinct melting temperatures, distinct properties, different from each other. That shows the complexity of polymorphic behavior of a single compound to be able to crystallize and give different properties as well as functionality. With this understanding, let me show the orientation of these chains in a single crystal structure so that we can have some basic understanding of how the acyl chains are oriented, which is shown here. Until 1990s, when this work was done, there were only 2 crystal structures that were known. That was C10 and C12 triacyl-glycerols. The reason for that is to crystallize these triacyl-glycerols into a good single crystal is difficult. That is why only 2 crystal structures are known. This is the triaryl crystal structure is shown here with the acyl chain orientation. Let me take you through the molecular orientation of the triaryl glycerol. The glycerol carbons are indicated here in red, 1, 2, and 3. And the acyl chain at 1 goes down, and the acyl chain at 2 goes up in a straight line between 1 and 2. And 3 acyl chain bends at the carbonyl and packs along the side of the 1. So when these 1 and 3 chains are packed together, the glycerol carbons axis or orientation is parallel to the N-methyl plane. So that is what happens when 1 and 3 chains are packed together. So in its single crystal structure, the same triaryl glycerol is shown here, projected along the b-axis. Here is the triacyl-glycerol, 1 and 3 chains together, 2 going up, and this triacyl-glycerol, 1 and 3 chains packed together, 2 going down. So they pack in a stacked chairs in a bilayer mode, as is shown here with 2 chain length structures, with the glycerol being parallel to the N-methyl plane. With that understanding, let us examine the homologous series of compounds that we synthesize, that PPX. How do they pack is shown here. This homologous series of compounds pack in 2 different modes in their most stable crystal form, in a trilayer structure as well as in bilayer structure. When the acyl chain is shorter, 10 carbons are below, the short chains segregate and form a middle layer, forming a 3-layer structure interposed by 2 palmitoyl chains and a shorter chains in the middle. But when the 3 acyl chain is a little bit longer, closer to the 16, they pack like a triacyl-glycerol in a bilayer structure, where 1 and 3 chains are together. As we have seen in the single crystal structure, when 1 and 3 chains are together, the glycerol packs in a parallel orientation, as glycerol carbons pack in a parallel orientation, as is shown here with respect to the N-methyl plane. But however, when it is a 3-layer structure with the 3rd acyl chain segregates and 1 and 2 chains packed together, this forces the glycerol conformation to take a perpendicular orientation to the N-methyl plane, as is shown here. So what is the implication of the glycerol packing in a parallel to the N-methyl plane or a perpendicular? What does it make a difference is shown in this slide here. We took 2 pairs of triacyl-glycerols, which is, this pair is asymmetric, this pair is symmetric. Both of them divolyl palmitin, but the palmitin in this one is at the 3 position. Here it is in the middle position of the glycerol. So when the saturated chains are at the 3 position, they pack differently than from the 2 position. I will show you in the middle here. As these triacyl-glycerols pack together, they form a tri-layer structure with the saturated chains segregate and form a middle layer with the volyl chains pack on the top and bottom, as is shown here. Similarly, here as well, the saturated chains are in the middle and the volyl chains are on the top and the bottom. However, here the saturated chains are attached at the 3 position. That makes the glycerol orientation perpendicular to the base methyl plane. But here in this pair of compounds, they are parallel to the N-methyl plane. So when we look at both these pairs of compounds, everything else is exactly the same. They pack in a beta substructure. The only thing that differs is the glycerol conformation. How this reflects in the physical properties of these materials is shown on the top. If we take the OPO and OOP, the symmetric compound has higher enthalpy and higher melting temperature, whereas the asymmetric compound has a lower enthalpy and lower melting temperature. That shows when the glycerol conformation is perpendicular, it is a higher energy state than the glycerol, which is parallel. This has an implication in the real systems like the phospholipids, where the polar function which is attached at the 3 position of the phospholipids goes up in the bilayers, and with the 2 acyl chains in the bilayer takes this glycerol perpendicular orientation. That is the implication that we can show, that this has a relevance to the natural systems. Having shown that, before I conclude the first part of my presentation, I would like to present a couple of important achievements that we accomplished. They are solving the single crystal structures of 2 mixed triacyl-glycerols, mixed acyl chain triacyl-glycerols, and also how the stereospecific SN-glycerols influence the metabolism. Those are the two aspects I would like to address. With that, the single crystal structures of the two mixed acid triacyl-glycerols is shown here. At this point, I would like to bring up my association with Professor Kiyotaka Sato of Hiroshima University and the collaborations I had with him and his colleagues. He is a good crystallographer. So one of the things I also thank the AOCS is our meeting was at the AOCS national meeting in 1986 in Hawaii. Since then, we collaborated together and published extensively. These two single crystal structures are part of that collaboration. Here, what I'm showing is the mixed acid triacyl-glycerol PP2. The molecular orientation at the atomic level structure is shown on the left with the 1,2 dipalmityl chains and the short 3 acetyl chain. And the same PP2 is projected along the A-axis is shown here, the unit cell of monoclinic unit cell having two molecules present in the unit cell where the 3 acyl chains are segregated and formed a middle layer interposed by 2 layers of palmityl chains. That gives the glycerol, once again, perpendicular orientation. With that understanding, let me talk about the second structure second single crystal structure that we solved. That is PP14, that is 1,2 dipalmityl 3 myristoyl SN-glycerol. Here, I would like to emphasize to solve the single crystal structure of beta prime is very difficult. The reason being, the beta prime is a metastable state. It is not the most stable crystal structure. However, because of the structure of this particular tag, beta prime happens to be the most stable. That is why we were able to crystallize this compound in beta prime form and solve first ever beta prime structure. And this compound packs in the hybrid subcell, orthorhombic perpendicular subcell, which is shown here, with two asymmetric units A and B of the same compound. And to facilitate this orientation of the chains, the acyl, the glycerol orientation is also quite different, that is shown in the right side. With that, let me talk about a little bit about the triacyl-glycerol, stereospecific triacyl-glycerol influence on the metabolism. Before I do that, let me give you a short primer on lipid digestion. The fat, when it is ingested, the triacyl-glycerol molecules gets digested in the small intestines by the lingual lipase as well as pancreatic lipase that cleave the primary esters of the triacyl-glycerol into 2 monoacylglycerol and 2 molecules of free fatty acids. These molecules get emulsified and they get internalized through the brush border membrane to get into the enterocytes. Then the enterocytes resynthesize the triacyl-glycerol and package them into a big particles like shown here, which are called chylomicrons. These chylomicrons get secreted into the lymph and they get metabolized into the lipoproteins LDL and HDL and so on. So that is the pathway of lipid metabolism. While I was synthesizing this stereospecific SN-glycerols, one of my colleagues, Professor Trevor Redgrave, fed these triacyl-glycerols with radioactive tracers to the first rat and then cannulated their lymph ducts to collect the chylomicrons and analyzed those chylomicrons and injected them into the second rat and looked at the disappearance of the chylomicrons, how they get metabolized. So when we fed the various triacyl-glycerols, what we observed was both the absorption as well as the chylomicron disappearance from the blood differed based upon the structure of the triacyl-glycerols. Here on the right is shown how the chylomicrons disappearance when fed with triacyl-glycerol OSO versus OOS is shown. The disappearance of the chylomicrons from the blood plasma were different for both these triacyl-glycerols. So that shows the triacyl-glycerol structure influences their metabolism. This was done about 35 years ago. At that time, this is one of the unique studies. We were able to prove how the structure of the triacyl-glycerol influences the metabolism. With that, I conclude the first part of my presentation. Now I will switch to the second part. That is new product development, which is shown here. To create a new product for a given application, understanding the molecular origin and connection between the structure, properties, and functionality of the materials involved is very important. Then we could be able to leverage that connection between the structure properties to create the functionality we desire. And the way it is done is, for any given application, there are some certain functionality requirements. Those functional properties are derived from the physical properties of that material. And in turn, these physical properties are derived from the chemical structure. So this chemical structure, if it does not provide the right functionality, then we could be able to see which properties are responsible for it, and those can be readjusted by modifying the chemical structure of the material. To make this point clearer, I'm going to show here the molecular properties of the natural oils listed here, and the derived functionality is shown on the right. For example, the natural oils have the molecular properties of reactivity, unsaturation, chain length, saponification value, acid value, and so on. And the derived functionality looks like appearance, viscosity, volatility, low temperature flow properties, and so on, given here. These properties are these functional properties are derived from the molecular properties. As an example, if you want to modify the low temperature flow properties of the material, this is connected with the molecular properties of unsaturation, chain length, polarity, molecular weight, molecular packing, and heterogeneity. So if we do not have the right low temperature flow behavior, we can be able to modify these properties or this chemical structure that is responsible for each one of these molecular properties or all of them. If we modify, we could be able to modify the low temperature flow behavior. So with that understanding, our thought process of creating the desired functionality that was lacking, we could be able to create the new products. So in the industrial applications, one other thing that we have to be mindful of is we have to understand what are the market drivers for these new applications. We have to understand before we go on and do it. When we were doing the fundamental studies, we don't mind about their cost, but here cost is very important because we have to make a value-added product, like making a gold out of lead, but not the other way around. So that is very, very important. Followed by the performance of the material and the availability of the raw materials, regulations that control the products, and the environment, health, and safety concerns, and the green image. If we can take into consideration of all these market drivers, we could be able to understand the market opportunity before we go on and create that new product. Here, I'm going to talk about the lubricants and how we were able to make the natural oils to work as good lubricants is shown here. Various functional properties required to act as lubricants is listed in the below. Natural oils inherently do provide some of the functionality without any further modification. For example, they do provide excellent boundary lubrication, They have good viscosity and viscosity index. They have high flash point, and they are biodegradable and non-toxic. They are environmentally friendly, and they come from the renewable materials. All this is well and good. However, two other functional properties which are very important, they do have deficiency. That is oxidative stability and low temperature flow properties. If we could be able to fix these two, these natural oils could be able to function as lubricants very well. So these two properties are interconnected. Let me show how they are related with each other. With this example of 4 different triacyl-glycerols, which are C18 carbon length triacylglycerol tristyrene, which is saturated, then monounsaturated trivoluene, trilinoleane, and trilinolenane. Their melting temperatures and the oxidative stability is given here. If we take the saturated tristyrene, it melts at 74 degrees. It is a solid having the flow properties of nil. However, if we go to the trilinolenane, its flow properties are excellent. However, the tristyrene has excellent stability, oxidative stability, because it is a saturated material, but this unsaturated material have very low stability, whereas these mono and disaturated materials have intermediate properties. So what I'm saying is, if we want to make a good lubricant, we should have the flow properties of a trilinolenane, but have the oxidative stability like a tristyrene. That is what we have to achieve. To understand this well, the nature has solved this problem already. As you can see here, it introduced a double bond, a kink, cis double bond in the middle of the chain of a tristyrene to make the trivoluene. Thereby, it dropped the melting temperature of about 70 degrees from going from tristyrene to trivoluene, as you can see. So if we could be able to do very similar to that, create a kink in the middle of the chain, will break the molecular packing to give the right flow properties, and it is saturated, therefore it will have the good oxidative stability. How we accomplished this is shown here. We converted these double bonds into cyclopropanated oils, cyclopropanated groups, by reacting with carbene, by doing a Simon-Smith reaction, which is shown here, and that put a kink in the middle of the chain, and that provided the flow properties. This material is flowable up to minus 40 degrees centigrade. Because this is saturated, it has very good high oxidative stability as well. So we solved the problem of both the oxidative stability as well as low temperature flow properties simultaneously. So it was very successful, we thought. However, we were not able to commercialize this material because the cost of this material, because of the expensive reaction, is prohibitive. So we were not able to commercialize this. This is something akin to the operation is successful, but the patient died kind of thing. So we want to apply different kind of approach to create a material that can be commercialized. So we looked at the heterogeneous to create a heterogeneity within the molecule, within the composition. The way we have done is we wanted to create the heterogeneity both at the acyl chains as well as the backbone by reacting with different polyol esters. The way it is done is the high oleic oils are transesterified with the polyol esters. Various polyols that we have utilized is shown here: neopentyl glycol, trimethyl propane, pentaerythritol, which contain diesters, triesters, and tetraesters. These molecules, when they are esterified, they give a family of bio-based synthetic esters that were useful, which I will show in the next slide, the chemistry of it. These products were cost effective and they were commercialized. The chemistry that goes on is given with the examples of taking a high oleic oil, transesterified with the trimethyl propane triethyl hexanoate under the basic conditions at higher temperatures, creates a composition having different head groups, as is shown here, and heterogeneous chain lengths and branched chains, as well as a little bit of less unsaturation. Most of the chains are saturated. Therefore, we created a family of synthetic esters called agri-pure esters. These provided the right features that are functional as lubricants. The salient features of these molecules are shown here. They showed excellent low temperature fluidity up to minus 25 degrees. They have excellent oxidative stability, very high viscosity index, range of viscosities depending upon which polyol ester has been used, and also the stoichiometry of the reacting materials. They showed low volatility, good boundary lubrication, and they are readily biodegradable, and they are cost effective as well. So that is a successfully commercialized example. With that, let me switch to the plasticizers. That is another application that we tried, which I would like to show today. The commercial opportunity for the bioplasticizers is shown here. The plasticizers market size is huge with $20 billion per year. And most of these plasticizers, more than 90%, are used in the polyvinyl chloride polymers. Currently used plasticizers are petroleum-derived phthalates, which have some environment, health, and safety concerns. So we thought we will have a good opportunity if we can create a cost-effective bioplasticizers. With that in mind, let me give you a brief introduction about PVC. Here are shown various PVC products that we use in day-to-day life. PVC is a very hard plastic, as is shown here, used for the pipes. And the same PVC can be made very flexible by compounding the PVC with the plasticizer. We can be able to make very flexible saran wraps. So the material that gives that flexibility is the plasticizer. Let us see how this plasticizer's function is shown here. The PVC polymer structure is shown here. It has two regions. One is ordered crystalline domain, as well as the amorphous chains that are shown here. When this polymer is mixed with the organic liquid and compounded well, then the small molecules, organic molecules, get embedded in the amorphous regions without any covalent bonding. They lower the glass transition temperature of the polymer, thereby imparting flexibility to the polymer. That is how the plasticizers function. So with that understanding, based on the literature, we came up with a hypothesis. If we want to synthesize a successful bioplasticizer, the bioplasticizer should be a fatty acid ester derivative having these molecular features that are given here. They should be low volatile and colorless and low viscosity liquids, and having a molecular weight of 300 to 500 Daltons. And they should have good PVC compatibility, having the molecular features of branching, ester epoxy function, balance of hydrophobicity and hydrophilicity, and of course, above all, they have to be cost competitive. We did synthesize we synthesized over 200 compounds, and we were successful with one series of compounds. They are the glycerol epoxy histolide fatty acid esters, and synthesis of which is shown here. We took the glycerol fatty acid esters and converted them to the epoxides by reacting with the hydrogen peroxide in the presence of a catalyst. Those epoxide groups are partially ring opened with the acetic acid and converted them to the acetyl derivatives called the estolides on the acyl chain. So these are the glycerol epoxy histolide fatty acid esters that were tested for as plasticizers. Our partners, Evonik and BASF, were the ones who evaluated them as bioplasticizers, and they found the properties shown here. Here, the evaluation plasticizer functionality is shown in a spider diagram, where the commercial plasticizer diisononyl phthalate properties are shown in red, and our experimental bioplasticizer properties are shown in yellow. And the experimental bioplasticizer properties are comparable to that of the comparable to the commercial plasticizer, and therefore this is a successfully developed bioplasticizer having a cost effective of cost of about 75 cents per pound. That is according to our calculations, and therefore this is one of the successful applications of development of our materials. That concludes my presentation. Let me summarize what I presented. Various SN-glycerol derivatives were synthesized and characterized. The systematic studies of homologous series of compounds showed how the chemical structure influenced the molecular packing and properties. This led to the fundamental understanding of the relationship between the chemical structure, molecular packing, and properties. We applied this molecular understanding to make value-added products useful in applications such as lubricants and plasticizers. Before I conclude my presentation, I would like to acknowledge my collaborators over the last more than 40 years, whose names are given here. I also would like to express my special thanks to Lucas Stahl, who also contributed part of this work and also helped me to put this presentation together. With that, I thank you for your kind attention, and I will be happy to answer if you have any questions.
Thank you very much, Dr. Kodali, for an inspiring and always informative talk. I think your approach to the chemistry of lipids and the physics of lipids is the one that exemplifies the Stephen Chang Award the most. He was always very concerned about this relationship between fundamental research and applications, and that embodies the spirit of the award more than anybody that I've seen before. So thank you very much. I do have a couple questions on the list here, and I'll start with somebody who had a very specific question. There have been some alternative reagents to the Simmons-Smith reagent, such as dibromomethane or diazomethane. Did you explore any of these reagents to cyclopropionate triolene to make a lower cost material? Can you comment on their effectiveness or cost saving, if you did?
Yes, while these products were developed while while I was working for Cargill, we did explore all the various possibilities of creating these cyclopropionated oils, including the biological approaches. Instead of diiodomethane, yes, we could be able to use dibromomethane, or even use the chloroform. Actually, could be able to we could be able to reduce the cost somewhat, but still the cost of the end product is prohibitively expensive for an application like lubrication. So if the application supports the cost of the material, then it would have been successful, but not for lubricants.
Great. Thank you very much. I have another question here, and in terms of, I found extremely interesting the difference in fatty acid chain length and the transition between a 3L and a 2L structure in the triglycerides. That was really, I know you explored 18 carbons, you explored 10 carbons. Did you explore anything in between so that you could say that there's like a maximum difference in chain length before that transition happens? Do you have to have 10-18, or does it still work with 12-18 or 14-18? Is there a break point there, or will depend on other factors?
let me go back to one of the slides. I'm glad that you brought this up because uh, um, this is very important point. Let me go to the actual slide. Um, I forgot to mention that breakpoint when I mentioned about this series of compounds. This is exactly what you were talking about. Can you see the slide? Can you see the slide?
Yes.
Okay, here is the breakpoint which I missed to mention. The X carbon number is shown here, 2, 4, 6, 8, and 10, and the X is 12, 14, and 16. The breakpoint is 10, exactly at 10. The trilayer structure goes into the bilayer structure. That is the breakpoint where the acyl chain length segregation stops, and the 12 and 14 chain length structures are accommodated in the bilayer structure. I forgot to mention about that. I'm glad that you brought this up. Yes, that is the breakpoint.
Oh, fantastic. So, I mean, it's quite a large difference. It's almost half the length, right? And then it starts segregating out.
Right. Because energetically, if you do create a shorter chain, there will be a bigger hole that is not energetically possible. That is why they have to segregate and form a middle layer in the most stable crystal form. And whereas in 12 and 14, it was able to accommodate, that is why it forms in the bilayer structure.
Great. Thank you. I do have one more question. I found that work was extremely fascinating, the digestibility, if you want to call it that, of OSO versus SOO, depending on the stereospecific position of the lipids. That leads to all the modern thing. People probably are looking more into it because that affects digestibility, right? And everybody's so concerned about the metabolic effects of triglycerides. I mean, what would it be if we had a diet richer in OSO versus OOS? You know, how would that affect us metabolically? And I just wanted to ask you, you know, the human milk fat and a lot of mammals, they put the saturated fatty acid in the middle, right? And that was a big, remember how they were developing human milk fat analogs, and there was a big debate of putting the saturated in the middle. Is there a reason, I mean, is there a difference between, and they were talking about palmitic always, but you're talking about steric. I do not know whether they're different, or why would a baby benefit more of having a slower kinetics than a faster? You would think that a growing baby, you just give them as much energy as they want, or is it a more complicated thing? What's your view on that?
That is a very, very, very relevant point. You were right. Milk fat contains this more saturated fatty acids, especially palmitic, and they also contain the shorter chain at the 3 position. If you look at the milk fat, it contains a lot of butyric acid, C4, C6 chains. Those are the short chains that get hydrolyzed fast because that is a primary ester, and they get absorbed very quickly. That is one of the reasons that shorter chain at the SN3 position. Also in this milk fat, the shorter chains are at the SN3 position, just like in the homologous series that I have shown here. So that has very straight relevant to the work that I have shown right here. The milk fat has that shorter chain at the 3 position that can be hydrolyzed and absorbed very quickly.
Oh, yes, of course, But why would the human milk fat and mammalian have the steric in the middle? So that would mean it's slower. Is there a reason, you think, why biologically we all of a sudden have all these saturated in the middle? Do we want that quick release of saturates, or maybe for absorption, right? Or maybe it has nothing to do with kinetics. It's maybe absorption.
Yes, this only the 2 saturated. I would say usually you are right. Actually, in the milk fat is an exception. There is a saturated chain at the middle, but they get once they are cleaved, 1 and 3, the primary esters are cleaved. It is the 2 monoacylglycerol that is gets emulsified and gets internalized to cross the brush border membrane, and then gets resynthesized into triacylglycerol.
Right. And having free fatty acids could lead to losses, right? They become soaps and they become insoluble, and the baby doesn't get the saturated fatty acid then. If it was all in position number 1 or 3, it would get hydrolyzed much more readily, right, by the pancreatic lipase. So that would be wasteful. That would be wasteful. And sorry, one more question since I have you here is, so what's your view? You talked and you mentioned a very interesting thing about diglyceride oils, and you just mentioned it in passing, the diglycerides, consumption of diglycerides having metabolic effects. You know that there's companies that have produced diglyceride oils like Innova from KO and stuff.
Yes.
What's your view? Is it safe to consume a lot of DAGs? Is there any issue with, imagine if your oils would all be diglyceride oils. Would you consume it? Would you be concerned about consuming a lot of diglycerides instead of triglycerides?
Definitely, the diglycerides are part of our oils. Actually, all the oils do contain, especially the palm oil does contain the diacylglycerols in some proportion. Maybe smaller in number, maybe less than 10%, but the palm oil does contain diacylglycerols, and diacylglycerols have lower calories than the triacylglycerols, obviously, and there is no adverse effect of the diacylglycerols by themselves. However, in the production of the diacylglycerols, there is a problem of creating those what do you call them?
The glycidyl esters or the MCT.
Glycidyl esters, yes. Yeah, formation of the glycidyl esters because of the process conditions, not because of the diacylglycerols. Diacylglycerols by themselves are good, but however, if any part of it gets converted to the glycidyl esters, those are the bad actors. Therefore, if you could be able to eliminate the glycidyl esters, the diacylglycerols are good for metabolism and there is no problem. Actually, they are lower calories and they do offer more benefits because they don't get deposited in the adipose tissues as much as the triacylglycerols.
Thank you. And I just do have one last question regarding your functionality and molecular structure. I think you forgot one. Or maybe it's so secret you don't do it. Maybe there's many others that we have forgotten. And in the application of lubricants and the use of oils, I never saw, and I'm facing this problem now, is compatibility with polymers like nitrile seals. It is a great challenge to actually have, many people want no effects of their lubricants on the swelling of nitrile rubber seals that are around. I just wondered, did you ever have to answer this question? Did you ever have to work on the nitrile rubber or other rubber compatibility of the lubricants you were looking at or not?
That is definitely one of the concerns, that is called swelling of the gaskets and those kinds of things as well. The lubricants going and swelling the gaskets, thereby affecting the creating the leaks wherever it is. That is why these ester lubricants, we have to make sure that they do not get absorbed by the polymer where the seal can be broken. That is one of the problems. And in evaluation, they do look at the seal swelling, one of the evaluation criteria. And our materials did not do it. These oils, they do not do that unless they are more polar materials. Then they get absorbed and then they swell the seal.
Yeah, we found, even looking at biodiesel, if the biodiesel has polar impurities, the world changes. Yes. And I think because they're lower molecular world, higher diffusivity, and somehow maybe the solubility parameters match more that of the rubbers, but there's something a little bit, it's the purity, I think, of lubricants is very, very important for that.
That is correct.
Yeah. Well, I don't have any more questions. I would just like to thank Dr. Kodali for, as always, a very inspiring talk in so many different areas. And I would like to personally congratulate you for the great accomplishment of the Stephen Chang Award, and wish and demand that you do not consider retiring for the next 20 years. Thank you very much.
I wish so. Thank you very much, Professor Barangone. That is very, very kind of you. Very nice of you. Thank you. Thank you,
Right.
everyone.